Hello, now let's go for the next topic, which is the standard deviation. Okay, let's go to the standard deviation. Let me share the screen. Okay, we are right here. Let's go for the statistical evaluation of measurement data. Uh, let's go for the average or mean value. Uh, we have two ways how we can analyze, right, a function that varies in time. One way is by using the average, and the other way is by using the root mean square values. These are the most important one for us. Okay, for example, the average value of any periodic waveform is found by dividing the area under the curve of the waveform in one period t by the time of the period. This is the average. Let's do it. The definition that is found for average is area under the curve divided by the length of the period. Remember, this is for periodic function. Great. For example, we can use functions. In this case, the average is equal to 1 over the period times the integral for one period of this function f of t dt. Great. Okay. Perfect. Now, this is an example. This is a wave that is going in this way, and we're looking for the average value. In this case, according to this definition, it's going to be area under the curve. So this area is positive, and this area is negative. So we have 40 times 1, right? 40 area times 1 a second, correct? Is this area plus. Now this little area over here is going to be 20 times 1 and minus this area because it's below this 0. It's going to be 20 times 2 and divided by the total length. What is the total length? 4. Correct? And what is the answer? The answer is going to be 10 units squared. Correct? Perfect. This is again different ways how we can calculate the average. Imagine that we have sine cosine function. Like in this case, we have sine function. What should be the average? Well, let's use the formula for averages. And it's going to be 1 over the period times the integral from 0 to t of the sine function. And this is the amplitude. A naught is the amplitude times sine 2 pi t divided by the period by dt. When we do the calculations, the integral is found that the average is 0. Actually, you can see the average. The average is 0 from the figure and also from the calculations. Perfect. Remember, this is one way, but the most important one is finding the root mean square values. Great. Now let's go to the root mean square values. That's the form, right? This is the root mean square. In this case, a. It could be any quantity. It's equal to the square root of this function square, and we take the average of that function, right? And again, the symbol means that the average of the quantity within the bracket is taken. Okay, and for a given waveform, right, f of t, the root mean square value is found by using this expression. Okay, that's the expression that we're using, correct, when we're dealing with the function, right? Is the same as this one, but now this is using integrals. Great. Now, in this case, this is equals to, imagine that we're dealing with, again, sine function, the sine function. Okay, so it's going to be 1 over the period times the integral from 0 to t of sine function square. And we have this one and dt, correct? When we do the integral, of course, we get that this is equals to the amplitude divided by square root 2. It's different. Actually, this is the value that we use, for example, for the current, right? the voltage when we're dealing with AC circuit, right? Use this approximation, right, using the root mean square values. Okay, great. Now from here, we have that the root mean square value for this function is the amplitude. I mean, this is a periodic function, sine, cosine, right? Is equals to the amplitude divided by square root 2. Is equals to, again, 0.707 times the amplitude. When we are not dealing with varying time function, then the average is given by this quantity, right? When it's not periodic. So the average is gonna be the traditional way how we can find the average is just adding the quantities and divided by the numbers of sets of quantities, right? We represented this in this way, where again, these values x1, x2, and so on are the values of each reading, and n is the total number of readings. Right? This is traditional average that we have, and this is when we have periodic function. It's not periodic. Okay, perfect. Right, again, we use this one, this quantity that it goes actually right here, right? It goes from here, right? We use these functions. This function, we use this one right here, right? Correct, to represent the root mean square values. Perfect. Now, let's do an example to explain in detail what's happening. Right? Imagine that we have these distances, right? This could be like, imagine you have a spring gun and you are shooting red bullet, right? And we have the impact at these distances from the origin. Okay, it's like a projectile motion too. We can use it that way. And let's find the average. Okay, let's add all of these quantities and divide it by the numbers of quantities. In this case, is another 5. And the average is 71.3 centimeters. Great. Now, let's see what is happening. Again, this is the initial point. Those are the 0. And then these are in centimeters. We're in one direction. These are the measurements. You have projectiles, spring gun, right? And they are, and this is the position, correct, for each let's say bullet is right there. And remember what I did, we're measuring the distance, like for example, 69.2, which is this one right here, right? And we have the rest, more or less, to have an idea. Okay, remember what we found is the average. The average is 71.3. Okay, and that's the average. And what is that distance? Well, 71.3. Perfect. Now, let's find the distances, right, of each bullet to the average and find another average, right? That's going to be the distance, like in this case, all right? Those are the distances from each impact to the average position. And let's make another average, and we call this the deviation from the average value. Let's find that deviation, all right? Now, if we use this formula, this is the formula for deviation. It's going to be x, the value, right, minus the average. And this number indicates the departure of each measurement from the average value. Let's do it. So for distance 1, we're going to be 70.3 minus 71.3 centimeters equals to negative 1 centimeter, right? And so on. And we have for D2 is 2.3 centimeters. For D3 is negative 2.1. For D4, 1.1. And for D5 is negative 0.2 centimeters. Now let's find the average, because we're dealing with the a new average, okay? And the average is gonna be 0.02 centimeters. Actually, if we had hundreds of trials, this average should be 0. But the average right here, as you can see, that this time is not 0. There are more than 0 right here. Means what? In this case, we are dealing with the deviation, taking into account the sign. But now what happens if we change just the distances? The distances are just the magnitude. Remember, a distance is always positive. So let's take just positive values to find the average, the new average, or the deviation, right, from the average. Take into account again just the distances. In this case, we're dealing with distances or absolute values. Absolute values are positive in this case. Okay, let's do it. Okay, from here, look one more time when the mechanical approximation is about zero, but we don't have a zero right here. It's different from zero, of course. Now let's go for the average value of the deviation. In this case, we take again the absolute value or the distances, like in this case is distance, right? Okay, and give us more precise precision. Okay, perfect. Now the average value of the deviation is found by taking the absolute magnitude of the deviation, right? Absolute magnitude, correct? Like in this case, distances. And what do we have? Well, let's take the absolute values for each deviation, correct? And divided by the number of the trials, correct? As another average. Great, and what do we have? Well, when we substitute the values, it's found that that average, that's deviation, right? The average of the deviation is 1.3 centimeters. Makes more sense than this one, which is zero. Perfect. Now, let's continue. Let's go now to the standard deviation. We're dealing with deviation. The most important one for us in physics, right, is going to be the standard, actually in science, right, the standard deviation. The standard deviation is also known as the root mean square deviation, right, that we explained before. The root mean square deviation means we square the function, we add those terms, and we take the square root of that sum. Okay, perfect. Let's do it. The standard deviation is much useful statistically than the average deviation. Okay, the standard deviation is found from the formula. This is a formula. Standard deviation is equal to the square root of the sum of these deviations squared divided by n minus 1. This is from statistics, where it's coming in this way. Or we can use the way that we are dealing with the standard deviation is this deviation square plus this square divided by n minus 1. For our case, for our example, we have that the standard deviation is equals to 1.3 centimeters. Remember the deviation that we found before was 1.3 centimeters. Now this is the standard deviation is 1.7 centimeters. Okay, now how we can use, what is the meaning for this? Okay, let's do it. Look, this is the graph for the standard deviation. Means at the center we have the mean or the average, right? And if we're going to the right and to the left, right, we have the difference of one standard deviation. So means that if we are in the range of one standard deviation, about 68.2% of the trial is gonna be on this region, correct? Now, if we expand the range to two standard deviation, two to the right and two to the left, we have a new region, right? Means that our trials are gonna be in this region, and the amount is gonna be about 95.4%, right? 95.4% of the trials are in this region when we have two standard deviations and so on. Right? Actually, when we're dealing with measurements in physics, let's say the density of metals, let's say the gravitational acceleration, any quantity that is taken as the standard or true value is actually an average, correct? So the quantities are actually represented in this way. This is the quantity must be equal to the average plus minus the standard deviation, correct? For example, in our case, our measurements are supposed to be represented in this way. the length is equals to the average, which is 71.3 plus minus, right, the standard deviation, which is 1.7. Means what? In this case, means that 68.2% of our measurement is within one standard deviation range, right? One to the right and one to the left, and so on. That's the meaning. How we represent these quantities, right, in physics, and the meaning, right, using these graphs. Okay, perfect. Now, let's do an experiment with this information, and let's try to um, plot again this curve, right, that give us the standard deviation or distribution, right, standard distribution, and compare this to the experiment that we're doing, right, using data. In this case, we're dealing not 5 data, but around 20. 20 points is a good indication. Actually, the best way is when we have hundreds of trials, hundreds of points to get a beautiful curves like this one. Okay, but in the experiment, we don't have too much time. We don't have um, uh, uh, exactly too much time. We can use around 20. Around 20 is fine. We can get an approximation, the idea, what is happening, right, in this analysis. Okay, see you in the next video. Thank you.